So the next example that we're going to go over, it's also calculating the angle of twist of a shaft. But here, unlike the previous example where we had a step function where the diameter would change at discrete locations, here we have an example of a shaft with a continually tapering diameter. So here we're going to have to use the integral format of our angle of twist equation. We did a very similar problem like this in terms of axial deformation of a column, where the denominator of our angle of twist equation is going to be a function, and so we have to use, again, integration to solve for it. So here, just to lay out the problem, it's a continually tapering shaft. It's fixed at point B. It has a length L. The diameter changes from the value 2r, the radius changes from a value of 2r at the support at B down to a radius of r. Again, there's no hard discrete values here for this problem. They're all left in variable format. A single torque T is applied at point A at the free end of the shaft, and we have a unsupported length L. So again, we're trying to figure out phi A sub B, which means the angle of twist of point A relative to point B. And so let's just go ahead and get into the solution here. So the first thing that we want to do, again, this is shown in isometric three-dimensional view. I always think it's a good first step to get this into a two-dimensional view to make the analysis a little bit easier. And so I'm just going to redraw this continually tapering shaft in 2 dimensions down here. And so we know that we have an externally applied torque at point A, and based off the right-hand rule, if I put my right hand and I curl it in the direction of the shown rotation here, my thumb will be pointing in the direction of the vector that I want to draw in 2 dimensions. So here, right-hand rule means that the vector is going to be pointed to the left, and so I get an externally applied torque here. So I would mention that it's kind of unfortunate use of variables here. They use a capital T for the external torque. That's the same variable that we use for the internal torque. So just to keep things clear, even though they'll end up being equal to each other, I'm just going to put this as T sub 1 to identify that it's an external torque. We'll calculate the internal torque later on. We'll just use capital T by itself for that, or TAB. Maybe that's a better way to do it, TAB. But I just want to make sure that you don't get confused that when we calculate TL over JG, we're not using this external torque. We have to make a section cut, solve for the internal torque. Like I mentioned in this problem, they're going to happen to be the exact same value and the same sign, but that's not always going to be the case. So I don't want you to get confused on that for more complex problems. Okay, so we have our externally applied torque here. We have our support at B. It's fixed. If I wanted to solve for what the torque is here, the support reaction is here, I could run some of the moments about the x-axis, and I'd find that this support reaction has to counteract this externally applied torque. So it'll be T1 at A and a reaction of T1 at B. Again, it's a relatively simple problem, so I didn't bother summing the moments about the x, but that's how we would have gotten this value of T1 if we didn't know it intuitively. We know that the length of this column is L, and we know, let's see, label these points really quick, A and B. And the only other thing that we want to put on here is the geometry. We know that the radius at this point right here is lowercase r, and that over here at support B, the radius is 2 times that variable r. Okay, and that should be enough to get us started. So this is simply just our 2D diagram. And it's a lot easier to look at analytically than this 3-dimensional isometric view. All right, so the next step is we need to get our fundamental equation out at the forefront, because that's going to inform everything else that we do for this problem. So again, we're looking for the angle of twist, phi, and we're going to put down the general form of the equation and see if we can simplify it a little bit. So our general equation for phi is that is the integral from 0 to L of the internal torque as a function of x dx divided by the polar moment of inertia as a function of x times the modulus of rigidity g. And again, this is the starting point for all of our angle of twist equations. In the previous examples, it's been simple because the internal torque as a function of x has been constant. The polar moment of inertia has also been constant. So we've just been able to turn this into a simple ratio. That's not going to be the case here, but we can simplify it a little bit. So in this case, if we're trying to figure out which of these are constant, I mean, the easiest thing to do is to figure out whether or not the internal torque is a function of x or whether or not it's constant. I'm just going to make a section cut. So all that I'm going to do at some arbitrary distance x, I'm going to make a section cut. And we could just look at the free body diagram. So let's just say that we're going to keep the portion of this shaft to the left of the section cut. So I'll draw what my free body diagram looks like for that. So we're looking at T of x right now, and I have a portion of my shaft up into the section cut. We have our externally applied torque at end A, and we renamed that to T sub 1, which is fine. This distance here is x. We're going to find out that's not going to be consequential, but it's good to complete our free body diagram. I can draw our coordinate system as well too. All right, then the only thing that we're really missing is just that internal torque. And I'll just call that capital T. Again, the internal torque is different than the external torque. In this case, they're going to happen to be exactly the same value in magnitude, but it's important to realize that they're not always going to be exactly the same. What we care about is the internal torque, not necessarily the external torque. We only use the external forces and moments to allow us to calculate the internal forces and moments. So here, if I were to sum the moments about the x-axis equal to 0, I would find out that the internal torque is equal to the external torque. It's not dependent on x. It's not going to be a function. It's just going to be a constant value. So in other words, T of x in this equation right here, that's just simply going to go to a constant value of T. Okay? And more precisely, the internal torque is going to be equal to T sub 1. So I can put that down there. All right. G is going to be a constant as well too. It's always going to be a constant. We haven't had any examples where the material is a function of the distance. There might be different materials for different discrete elements, but it's never really a function of x. It's more of a step function. But here, we're not going to be able to get a constant polar moment of inertia. And so this will simplify down, but we're still going to have the integral form to it. So I'm just going to rewrite this equation, and I'm going to pull out the internal torque. I'm going to pull out the shear modulus, and I'll get that phi is equal to the internal torque, which is equal to the external torque, divided by the shear modulus times the integral over the length of dx over the polar moment of inertia as a function of x. Okay, so it's never fun having these functions in the denominator, but it's not that big of a deal. Everyone's had calculus, so we'll deal with it as it comes up. So G is just a material property. Again, everything in this problem is left as a variable, so we're assuming that we have G. We don't need to adjust that. T we've already determined is the internal torque is equal to the external torque. So we just need to figure out a formula for this internal polar moment of inertia. And so what we're going to do for that is we need to figure out an equation that represents the radius as it changes from A to B. Because again, this is how we solve for T. Let's just have a separate sidebar over here so that we can solve for the internal the polar moment of inertia as a function of x. We know that for a solid circular cross section, which is what this member has at every single section cut, we know that J is equal to pi over 2 times the radius to the 4th. Okay, in this case, the radius is no longer going to be constant, and so we need to put in a function for this value c. And so here, if we were to draw a diagram of just half of this member, we would see that at point A, we have a radius of r, at point B, we have this radius of 2r. And if this is x is equal to 0, with x going to the right, we just need to figure out a function where c is a function of x that gives us r is equal to 0 at a. The radius is equal to r at a. The radius is equal to 2r at b. And so I can break this up. It's just a linear relationship, so it's just a first order equation, relatively straightforward to calculate. But at any point x, I want to be able to calculate the radius as a function of x, or c of x. And let's see, this overall length right here is L, which is going to be important for deriving this equation. And so the equation that we come up with, there's a couple of different ways that we could go about it, but it's simple geometry, not even trigonometry at this point. So I'll kind of gloss over the actual derivation of the formula. You should be comfortable with point-slope format, determining the slope and the intercepts and everything else. What we're going to find is that the radius as a function of x is equal to r over L times the quantity L plus x. And so we can calculate this at a couple different locations just to make sure that the values work out. So if I were to plug in a value, c at x is equal to 0, all right, I would get r over L times L plus 0. And so the L's would cancel, and I would get a value at x is equal to 0. The radius would be r, which is this point right here. So that checks out. We can check out the last point as well, too. C at x is equal to L, which corresponds to point B right here. I would plug in those values. I would get r over L times L plus L. All right, that's going to have 2L in this quantity in the parentheses. 2L over L is just equal to 2. So I would get 2 times r, and that is the radius that we get at point B. Okay, so this formula right here will give us the radius at any given point x along the length of this shaft. Okay, so if that is the radius is a function of x, we need to take this and we need to plug it in to our polar moment of inertia equation. Okay, so it's relatively straightforward. Still just algebra at this point. I'm going to take this entire quantity right here. I'm going to plug it into this equation. I'm going to take it to the 4th power. So I end up getting pi over 2 times r to the 4th over L to the 4th times the quantity L plus x to the 4th. Okay, so that's what's going to end up going to my denominator of my angle of twist equation. This right here, all right, that is equal to the polar moment of inertia as a function of x. That's this denominator right here. So we're going to take this, we're going to plug it in right there. So again, if it's a constant inside of your integral, you can take it out as a constant value. You can take it outside of the integral itself, which is exactly what we do here. So I'm going to simplify this a little bit. I'm going to take out this pi r to the 4th over 2L to the 4th. That's going to be the denominator, so I can take it out, flip it over, and it simplifies a little bit to t over g as a constant outside of the integral times the value 2L to the 4th divided by pi r to the 4th. Again, that was the constant portion of our polar moment of inertia. Again, it was in the denominator, so when I pull it out, it gets flipped over and multiplied by the other constant t over g that we had here. And then I'm going to have my integral from 0 to L of dx over the variable portion of our polar moment of inertia equation, which was simply L plus x to the 4th power. All right, so I just need to evaluate this equation right there, and I'm going to get phi is equal to, I'll still have my constant value out front. I'm going to simplify it a little bit. It'll be 2 times the torque times L to the 4th divided by pi r to the fourth times the shear modulus times the quantity -1 divided by 3 times L plus x to the third. And this will be evaluated at x is equal to L. And it'll be evaluated at x is equal to 0. And we take the difference between the two. And this simplifies down with a couple of intermediate steps here. I'm not going to go through all the algebra. The algebra, if you want to see it, is provided in the solutions up on OneNote and OneDrive. We get that phi of A relative to B is equal to 7 times the internal torque times the length divided by 12 pi r to the fourth g. Again, you should be comfortable with the variable format solutions. A lot of times students only want to put in discrete values and calculate it all through. This way, I think, is a bit cleaner, and it avoids some of the errors that you get by losing significant digits as you go through the process. So you should be comfortable with the variable format. It would be fair game for an exam or a quiz or on the homework as well too, not just for this chapter, but for any chapter. So if this is our solution right here, you know, one thing that I've mentioned is once you get your answer, it's really important to check whether or not it's reasonable. So for example, if we had discrete values in here and we got a final answer of, you know, 4,000 radians or something like that, right, that should raise some red flags. You probably are off by an order of magnitude or maybe a couple here or there. Maybe you have a unit error as well. And so that's another reason it's nice to keep this in variable format, is that a good thing to do at the end of your calculation is to simply check your units. And so I'm just going to put in some examples of SI units here to make sure that everything works out. So 7 is just a constant value that doesn't do anything to the units. Capital T, that's in torque, so I'm going to put that in Newton meter. L is the length, so I would put that in meters. Divided by 12 times pi, just a constant value, no units to it. All right, radius to the fourth. We'll say radius is distance in meters, so it'll be meters to the fourth. And then the shear modulus, or the modulus of rigidity. That's the same units as we have for the modulus of elasticity. That's going to be in pascals or newtons per meter squared. Okay, so we can simplify this a little bit. We get Newton times meter squared in the numerator, and we get Newton times meter squared in the denominator. They cancel out. And so it appears unitless, but again, radians are a unitless value. So this is in radians. It works out in terms of units. Okay? So again, we went from our general equation for the angle of twist for a torsional shaft. We were able to take out some constants because the internal torque was constant. The modulus of rigidity was constant. But we still had to deal with the polar moment of inertia as a variable or a function of x. So once we do that, we had to integrate. We do the integration. We skipped a couple simplification steps, but at this point it's just relatively simple integration, so you should be comfortable with that. And we arrived at our final answer. We checked the units to make sure that it was reasonable. Again, on a homework, on the exam, on a quiz, you should be able to deal with either a non-constant torque or a non-constant polar moment of inertia. I probably wouldn't throw both at you at the same time. But again, this is the same format as NL over AE that we have for axial members. And so, I mean, everything in between is just calculus, and that doesn't change. And really the analysis and how it gets set up is really the same as well too. So if you know how to do one, you should be comfortable with the other. All that you're going to do is just change a couple of the variable names, and the units are slightly different, but the procedure is exactly the same.